Yeah, I guess if I turn that off, I'd say that the things that we're talking about this week are less relevant to you guys, all of you collectively as a discipline: environmental systems engineers, energy engineers, mining engineers, and petroleum engineers. Open channel flows, that is. But I guess it's part of a big water supply component. So the whole of LA, and I guess it's only 10 months ago, the big fires, the Eden Fire and the Palisades Fire in LA with the January or February Santa Ana winds. And of course, that area of the country is super dry, and it's only habitable because they get all of their water from Colorado. And so the western states, I guess, now is in a big crisis because rainfall is down, climate change is going on, and the supply that brings it across in the California aqueduct, which feeds LA. I guess San Francisco probably gets its water from Yosemite, the Tuolumne and the Yosemite area of the Sierras. But certainly LA gets it from Colorado, the Colorado River, and it's if you fly into San Francisco, you fly over portions of the aqueduct just before the coastal ranges. And so the big controversy is where that water comes from, who has rights to that. Colorado wants it more now because they are dry, snowpacks are down, and actually Chinatown, the movie, kind of a classic movie with Jack Nicholson in it, before your time, but it talks about the whole of the settling of the Owens Valley, which is what brings the water into LA after it comes across the mountains, and it's a story of intrigue that's set in LA. So again, I say the things we talk about in this class in terms of open channel flows are perhaps less relevant, and so we will talk about it today. Maybe tomorrow, on Friday, we'll talk about kind of a big picture summary of where we've come and how it fits into your different disciplines in large part. We made the point last time when we were talking about surfing West Virginia that the one thing that's different about open channel flows is that you have an extra degree of freedom, that the water chooses to flow either deep and slowly or shallowly and fast. And so understanding how that transition can occur is part of our job maybe today, but not part of our job on Monday, when we just talked about uniform flows, where the upstream level and downstream levels are the same. And so we'll start by finishing off that. We talked about Manning's coefficients last time, and then we'll move into talking about these kinds of flows, and more specifically, or perhaps more controllably, in terms of an orderly transition where we talk about hydraulic jumps, where, as we were saying before, it can flow very quickly upstream at a shallow depth, and because of continuity, the flow downstream, which is much deeper, has to be, by the virtue of the bigger cross-sectional area of flow, it has to be a slower flow. And we can talk about the mechanisms by which that can occur. So that's our job today. It's actually kind of a fun topic, actually, open channel flows, because you have the vagaries of this ability to flow in these two configurations. Go back to what we started talking about last time, just to remind ourselves. The big picture was that pipe flows, external flows, and open channel flows follow the same kinds of rules. They all represent some kind of energy loss in the system by friction. In pipes, that's friction along the wall of the pipe, which varies from laminar to turbulent flow. On objects, such as a falling sphere or a falling free-fall parachutists, it's flow past that body, which we're interested in, and we're interested in the force that's applied to that. Essentially, if you're falling through space, it's the force that's the air pressure on your chest as you fall at 200 miles an hour at terminal velocity through the air, which is a pressure on your chest, which is a force that's applied to the sphere, either as drag or lift. And that also follows from laminar behavior and turbulent behavior. And when we talk about open channel flows, we made the point that these flows are so wide that the hydraulic radius is so large that Reynolds numbers are typically very large as well. And so we only have to deal with the turbulent regime. So that was the case that we were making last time. We played around with some equations. We came up with a formula, the Chezy formula, for the case where the upstream and the downstream depths are exactly the same. And that formula was this. And this can always be used to calculate a velocity. If you multiply the velocity, average velocity within a channel, by the cross-sectional area of that channel, then it gives you a volumetric flow rate, which would be how water would be supplied to San Francisco along the California aqueduct, etc., if you knew these parameters. We noted that they had dimensions. They were not non-dimensional. They actually, the dimensions on the left-hand side don't match up with those on the right-hand side, and so we have to be careful of our units. And if we're working in SI units, we have a coefficient here, which is 1, and if you're in English units, it's 1.49. And you can basically plug and chug with these as long as you know what these components are. We made the case that we're always working the turbulent regime. The Manning's coefficient is large if it's a big drag. So if you have brush within a channel, making a drag on the side, on the water at the edges, then that Manning's coefficient is large. And if it's a glass line channel or a smooth concrete line channel, then it's relatively small. And so we can make those calculations. I guess these are just some notes on how you might apply it. If the channel is very wide and very shallow, then the hydraulic radius is approximately equal to the depth of flow, just because in calculating the area and perimeter ratio, as it goes to infinite width, that will asymptote to just the depth. If we have channels where you have some different materials on different portions of the channel, you can subdivide the channel to use different magnitudes of the Reynolds number and do the sum of those components, right? So we talked about, if you remember back this far, just a drawing to remind you, we talked about pipe networks. If you're flowing between an upstream and a downstream tank with pipes, we said that in doing this, the sum of the volumetric flow rates equals the total flow rate. And so that would be equally the case here. So if you sum the flow rate in this section plus the flow rate into the page in this section plus the flow rate in this section, you have the cumulative amount, which makes sense. If you have a compound channel, which is what this is, with different, even if they're the same Manning's numbers on the perimeters of these, when you sum them, I guess you have to be careful in defining this hydraulic radius, which you need to use in Manning. I don't mean to give you whiplash. We need to use a hydraulic radius in these, and also the area for the volumetric flow rate. I guess you need to be careful to rationalize the fact that the hydraulic radius is the incremental cross-sectional area times the perimeter, right? So for this area, this channel here, the perimeter would be, would be this, P1. It wouldn't be this as well. And the reason for that is that the water here is traveling at this velocity into the page. It's also traveling right next door at the same velocity. So there's no net drag between those two compartments. So the perimeter for this cell would be P1. The area would be A1. So to get the flow rate, it would be A1 times the hydraulic radius just using this perimeter P1. Likewise, for this one, the perimeter would be this, and the area would be this. It wouldn't include these two other steps here for the same reasons. And this is the slope of the basal bed just as a gradient, drop in height over length. So a big kayak river is 100 feet per mile. So that's 100 feet in 5,000 feet. So that's about 2% for a very turbulent river, like the ones we looked at, perhaps. And that probably wouldn't be uniform flow. So these values of gradient are typically of the order of perhaps a percent or so, 1 in 100. And we can also figure out what the most efficient sections would be, where the drag on the exterior would be the minimum for a given section. And it turns out that if you look at a rectangular section, the most efficient section is where the depth is equal to half the width of the channel. For triangle, it's equal to a right-angled triangle. For an arc-shaped channel, it's a full half circle that gives the best efficiency. And for a hexagonal channel, it'd be at 60-degree angles. So that's it. So that's Chézy formula. The midterm test, the final one, the flow question, this might be a good thing to look at. Of what we'll talk about now. So we'll talk about some other things which are more complex today, but the essence of the midterm final is related to uniform flows. And so a quick example here is just to be able to look at a channel which has a section given by this, just to show you what's going on. It's trapezoidal. The gradient is 1.4 feet in 1,000. So this would be the gradient of the bed, 1.4 over 1,000. It's got smooth concrete. I think we just looked at concrete in terms of the Manning's coefficient. It is, I don't know, finished concrete, 0.012 or 0.014. So N would be this. I think it's 0.14 that they use. I didn't. 1, 2, or 0.0. You know that you're always given these numbers. And the flow rate is just, it's in English units, so it's 1.49 instead of 1.0. Area, hydraulic radius, gradient. We have the gradient. We want to calculate the Manning's coefficient. So we have this. And we have to calculate the other two components. The area is 12 feet. It's 5 feet depth. Perhaps you can't see that so well. This is 5 feet. So this would be 5. This would be L 10 40 equals 5, and X sine 40 equals 5. So you don't know this length, and you don't know this length either. So you can get the area by being the area of the prism, which is what this is, plus 5 times this length. This length here is equal to 5 over tan 40, which is this. So L equals 5 over tan 40, which is what this is. So this length times a half equals this area. So 2 times that is just equal to this prism because it's on both sides. So that's what this area is. So this is the, should I draw it properly? So this is this plus this. So you have the area, and you can all do that. Hydraulic radius is going to be equal to RH equals 12 feet plus 2 times X. and x is equal to 5 over sine 40. This here, so you have a radius, and the rest is plug and chug. What did they use? They used this, smooth concrete. So the rest is just plug and chug. That's it. So long as you know each of the components in this equation, the Chezy equation, which is this, either for this is the average velocity, or this is the product volumetric flow is equal to the average velocity times the cross-sectional area. You know how to do that. So straightforward. Just plug and chug. So very formulaic. Okay? All right, let's do something more exciting now. So a couple of examples there. And again, just to make the point that I guess we divided this up, kind of. We did subdivide this up into these. Actually, we used a total cross-sectional area. I guess in this case, since the Manning's coefficient were the same on all the surfaces, we didn't have to do this. And automatically, the perimeter included only the wetted perimeter, not the internal perimeters, which we leave out logically because they're both traveling at the same velocity, and so there is no friction by Manning's coefficient in those parts. Okay. All right. So that's that. So let's look at something more more interesting. So this is the case where we have upstream and downstream are exactly the same depths. If they're not the same depths, then we have to do something else to deal with that. And of course, this could be merely, I think the figure repeats itself. This is the case we started off with. Uniform flows are the ones we've talked about so far, that upstream and downstream are exactly the same depths, and they don't change as you go from upstream and downstream. Gradually varying flows are where it starts off maybe deeper upstream and maybe more shallowy downstream. And we can use the analysis that we'll do for this to also say something about so-called rapidly varying flows, where it goes from something where it's very deep upstream to very shallow downstream. Or it could do the reverse, from going very shallow upstream to very deep downstream. So the way that we can look at those most conveniently is to just look at them under the rubric, if you like, of gradually varying flows. And we've seen this before. And so the difference is that as opposed to the case before that we had this elevation change delta Z over L. This is gravity, which is driving the flow. If the upstream depths and the downstream depths are the same, the cross-sectional area is the same, and therefore the flow velocities are the same. So the hydraulic grade line and the energy grade line have to be parallel to each other. And they also have to be parallel to this slope. So all three of these gradients, SF, SW, and S0, are the same. So SW is just exactly the same. This is this delta. I guess it could be, I suppose it should be delta Y. We can use it over L. So these are just gradients of these. If we look at gradually varying flows, there's no guarantee that if we go from upstream to downstream that the depths are the same, because they're not. So SW and S0 won't be parallel anymore. And I guess if we look at the velocity heads, then probably this velocity head is going to be larger because the cross-sectional area of flow is smaller. And so that's the rationale that we're working from. So, okay, maybe I'll come back to, I don't do these derivations, and I want to come back to that. So I guess I'm going to write some stuff, see if I get it right today. So we're going to talk about gradually varying flows. So exactly the case that we have above, which is when this is the case. Okay, so what's the easiest way to introduce this? We can start off with z equals 0. We can have the bed of the river, which gives us S0, and we can have the water surface on top of that, which should converge from upstream to downstream. And it was green before, so let's do it green again. And that is to have this. So this is S sub F. What did we call this one before? Can't remember. Need to remind myself. Didn't put it on there. SW, surface of the water, slope of the water. And so if we look at these, and I just used black, then this is, you could think of this as Z1. I'm going to draw this vertical, even though it might be parallel to the bed. So this is the bed of the stream. So this is Y1. This is Y2. And you remember for Bernoulli equation, we write it between upstream and downstream. That's all we're doing. This is V1 squared over 2G. This is V2 squared over 2G. And this is flat. And let's call this H sub L. So all of a sudden, maybe that looks a little bit familiar, in that if we write Bernoulli between upstream and downstream, we have Z1 plus P1 over gamma plus V1 squared over 2G plus HP equals the downstream terms. And this is the head loss. So this is equal to L in this direction. And so we can simplify this. So first of all, we don't have a pump in here. So we can set this equal to get rid of this. We can note that if we're sitting on the bottom of this stream, then the pressure at this point is equal to Y1 gamma W. And so P over gamma is just equal to Y. So this is Y1. This is Y2. I guess what else? We could gather terms, and let's do that. And if we gather terms, I'm going to keep these two expressions on one side. And so it'll be Y1 plus V1 squared over 2G is equal to Y2 plus V2 squared over 2G. This is G, not Y. Plus Z2 minus Z1. Plus HL. So one more switch with this. So let's, I guess I'm going to change the two other components. We've defined S0 as equal to delta Z over L. And so this means that delta Z is equal to S0 times L. And this here is minus delta Z, right? Delta Z would be Z1 minus Z2. This is the negative of that. So this would be minus S0 times L. This HL would be equal to, so this is a length, and this is dimensionless, right? So this is a ratio, so this is right. And this would be HL, and so we can also write this as SF is equal to HL over L. Therefore, HL is equal to SF times L. Okay, that's the last manipulation. The rest fits in just as before. So we're going to make this substitution. The other thing that we would like to do, since the elevation may be changing downstream, is to draw kind of a perspective cross-section of this flow. And this is flow into the page. And so this is, and so the components on this would be the width of the channel, which we'll call B, and the depth of the flow, which would be either upstream or downstream, which we'll call Y. And we'll have a volumetric flow rate going down here, which we'll call Q. And so what I'd like to do is divide this up into a segment, which is 1 unit wide, say 1 meter. And within this 1 meter, the volumetric flow per unit width we'll call lowercase q. Right? And so this is just volumetric flow rate in the whole section. It's of depth y and width b. The volumetric flow rate upstream and downstream is always going to be the same. But we'd like to be able to characterize exactly what this Q value is as a flow rate per unit length. And so the easiest way to do that is just to realize that the volumetric flow rate per unit width is equal to the total volumetric flow rate divided by B. Total flow rate, the amount flowing over this section is just this. And so the flow rate Q is going to be constant in any length downstream. And we can also write the velocity within this portion is going to be equal to Q divided by Y. So the flow velocity, the average flow velocity, is going to be this magnitude here. So we could write this as constant. So what we could do with this is we can define velocity as being equal to Q over Y. I guess I'm just rewriting it. And the utility of that is that we can write this expression in terms of these velocities here. Because as we go upstream where the depth is equal to y1, and I can't draw it very easily, but downstream the depth is going to be y2, this velocity term is going to be conditioned by a value of the volumetric flow rate per unit width, which is going to be the same by continuity. So the final perturbation of this, I guess, is to take this whole equation with these extra terms, substitute in for v as this, and it would come out to be y1 plus q squared over 2g y squared, right? So q squared over y squared is just the velocity squared. This is equal to the downstream component, which is the same flow rate. Upstream and downstream, this value of q has to be the same, but v won't be the same because it's going through a different height. So this is what we have downstream, but this is 2 times gravity times y squared. This is the downstream depth squared. And this is minus S0 times the length. So this is the gradient of the bed plus the gradient of the energy line times the length. And so we can write this in shorthand as specific energy E1, which is this, plus specific energy, sorry, not plus, equals the specific energy downstream plus minus S. I'm going to put these together. I'm just gathering these two terms together and writing them backwards so I can have a positive here. And so this is the specific energy that's present within the system. And so this allows us to be able to say that maybe upstream the energy is equal to E1, maybe downstream the energy is equal to E2, and if there's nothing strange in the middle, in fact, if these if we ignore this gradient term here, they should equal each one, and we can do a match between them. And so this basically says that we can define that as we go from upstream to downstream, the magnitudes of these should be the same. Okay? So let's have a look at some of the pictures. I'll come back to that in a sec. Yes, Nicholas, I hear you talking.
Yep.
Hit me.
Okay. You want me to use it? So would lowercase q in this case represent the flow over the total area, whereas
Uppercase q is the flow over the total area, total cross section. Lowercase q is the flow over 1 meter or 1 foot width, which will be the same per 1 meter width upstream or downstream, but the velocity of that will be larger downstream if it's shallower, and it will be smaller. The velocities will be different upstream and downstream. That's what we're doing.
Okay.
And so we're defining this. So we need to keep these things present. So what we could do, I guess that's what I was checking on because I couldn't quite remember. We're okay so far. We have the right expressions. So he's saying as we're going upstream to downstream, so if we drew this along the length, as a most dramatic version of this, we could have a weir. This wouldn't really be a gradually varying flow, but you get the picture that this could be y1, this could be y2. This is probably a rapidly varying flow rather than gradually varying flow, but this is the idea that it can change from upstream to downstream. So this energy we can equate between upstream and downstream. So what we could also do is we could rewrite it as upstream or downstream, and it's equal to y1 plus q squared over 2g y squared. I don't want this. This can be any depth. And so we could rewrite that as a quadratic that is equal to 0 is equal to minus e plus y plus q squared over 2g y squared. And I suppose to make life easy, we could multiply both sides by, that's 0, by, what do we want to do? Y, yeah, okay, is equal to e y squared plus y cubed. So if we multiply this by y squared, top and bottom, top rather, then it is equal to q squared over 2g. This is cubed, right? And so this is a cubic equation. And so all we've done is multiply it by y squared. So we have a power to the 0, a power to y squared, and to y cubed. And so this has 3 roots. Quadratic has 2 roots, linear has 1 root, and cubic has 3 roots. There are 3 solutions for y. So what we could do is we could plot the 2 terms that turn up in this. We could plot energy. So this is, we haven't defined it, this is specific energy. And we could plot depth of flow, which we'll call y. And we presume that if it's really shallow flow, the depth would be 0. So what we could do is we could choose y is bigger than 0 and less than infinity. And we could use that to calculate E. So here we have E as a function of y, Q as a constant. So the flow coming down our channel is constant. Gravity is constant on this planet. If we change y, then we get a value of E. And if we plot that, then it would look like this. It would look, I'm not very good at drawing this, it would look something like a nose, basically. It would asymptote at the bottom to flat, and it would have another portion here. And so if you look in your flow, that energy is constant. So E equals constant. This would be the equation, these black lines would be the equation for Q equals, I don't know, 5 meters squared per second, right? So what's Q? Q is equal to the volumetric flow rate divided by the width. So this would be Qmex, cubic meters per second, divided by meters. This would be meters squared per second. So in your channel of a given width, we can always calculate what this is. If we know what this is, or rather, if we know what this is, we can always calculate this. And these are the 3 roots. So these are the 3 plausible solutions to this equation. It could be this depth, it could be this depth, or it could be negative depth. Can't be negative depth, doesn't make sense. So these are the 2 routes that are viable. And the cool thing about this is that this represents our flow system. Are you wondering what this looks like? This is our system. Upstream, Y1. Downstream, Y2. It was for gradually varying flows, I guess we said, but we're co-opting it for this. And so these individual depths are given by these potential solutions to that problem. It's kind of cool. So this means that it can travel at this, it can be present at this velocity. This would be Q, and this would be Q. These would be the same. This would also be Q, lowercase q, and this would also be lowercase q. But this would be V1, and this would be V2. And V1, in this case, is much less than V2. They're not the same. These are the same. So Q1 and Q1 and uppercase Q, lowercase q1, and uppercase Q2 and lowercase q2 are the same, but these aren't. And they would be this. I just chose a number. We didn't do an example. So that's physically what it represents. And so the other part of this, I think that's fascinating, is that this is orderly, and this nose here, the part that is furthest forward, is we will call the critical depth, y sub c. This is not gc, it's yc. And this would be the minimum energy, E min, that this is moving at. So this particular nose has these properties. And these two flows represent what we would refer to as a subcritical flow velocity flow and a supercritical velocity flow. And so this critical depth here would be the transition between the two. And so the other cool part of this, I think, that relates to this, maybe it's worthwhile looking at the drawings that I have that perhaps try and explain this. Yeah, so this is the idea. So this is kind of our upstream behavior here. It's deep, it's flowing relatively slowly, and this is less than the critical depth, which is y sub c, the point that's on the nose of our diagram. If it's flowing critically, the Froude number is equal to 1, which we'll revisit in a second to see what that means. And so we can define a depth. The depth we define is exactly the depth of this nose here. And I guess the point is that at this particular flow velocity in a system, it could flow either slowly and very deep, or it could flow very quickly and shallow, and we don't really know how to choose between them because they can both happen. And so it matters which side of this critical point we are, and that relates to some other parameters in our system. So this is the figure that explains that. It could be reversed as well. Hydraulic jump, fast flow upstream, all of a sudden jumping to be deep flow, slow flow downstream. It's just the opposite of this. But it's the same idea that in going from subcritical to supercritical, or the other way around, we have to go through this critical depth. And so how do we define that? Well, it's defined in terms of the Froude number. And the other cool thing about that is that, so this would be subcritical. So this would be, we've defined this Froude number. It's equal to the flow velocity divided by the velocity of the, do we call it Vs or Vc? The velocity of the celerity wave. The celerity wave is the velocity of the, if you drop a stone in a pond, the velocity of the ripples that come out of that is the same as a tsunami. And Vs, we know, is equal to the depth of flow, which we'll call y, multiplied by gravity square root. So this is the same depth that we're talking about here. So this is the speed that water will flow at. It doesn't actually move, right? It just transmits information. So you know that a wave, rather than moving that packet of water to downstream as the wave goes downstream, it just rotates in place, and the momentum of that shock is moved downstream. It's kind of like a line of railway cars being shunted by the locomotive at the end. The end car doesn't all of a sudden become the beginning car, but it hits at the end and it goes boom, 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 and then hits this. It's a transfer of energy downstream, not a transfer of mass. And the kind of cool thing about this is that the Froude number changes from the numbers we talked about here. Should make sure I get it right. That the Froude number at this nose is equal to 1. So the ratio of the velocity of the surface in the subcritical flow is less than 1. And so this is for the deep flows. So this is subcritical above the nose, and it's supercritical for the shallow flow below the nose. So I guess we can write this. So if we go this, so in other words, this point here, Froude number is equal to 1. Froude number is less than 1. And below this point, I know it's getting to be a complicated diagram. And by the way, this is not on the test, but it's cool stuff. And so the numbers on this curve, if you calculated what the velocity was relative to the depth of flows, which occur in this, then the Froude number would change from 1 to being 0.9, 0.8, 0.7, 0.6, 0.5, and it would go from 1 to 1.1, 2, 3, 4, 5, 6, 7. So this. And the kind of cool explanation of this, with 5 minutes left, is that it defines kind of the rate that information gets sent upstream. So if you imagine this weir not being here, but this just being a wall of water that's foaming over, just like in the hydraulic jump when we switch this around. Shallow fast flow going into a big pile of water downstream for a deeper flow. There has to be some information that's exchanged from the upstream to from downstream to upstream to let it know what's going on. And so if we look at the velocity of flow being equal to 0, then if you drop a pebble into the water and look at the radiation of that pebble at time 1, time 2, and time 3, going outwards, then these ripples would travel at the velocity of the celerity wave, which is square root g times the depth of flow. So this is where the velocity of flow of the water itself is equal to 0. If you imagine the case where the velocity of flow is less than the velocity of the celerity wave, and you drop a pebble into the water off a bridge, and you think about where those ripples will go relative, I guess you could probably think about just keeping on dropping pebbles into the water all the time, then all of a sudden it won't be concentric. If I do it fast enough, it'll do it as a thing. It'll be a circle, but it won't be concentric, so that's not a circle. That's not bad. That's pretty bad. Oh. I thought Control Z might undo it. So you get the picture, right? It's going to get bunched like this. Great. Oh, Fantastic. That's what it looked like. You could think about just dropping pebbles in. The reason is that this is going downstream at some flow velocity, v flow not equal to 0, and therefore it'll look like this. If you throw it in at the flow velocity is equal to the wave speed, then it will look like pebble in, yeah. Imagine that's a circle. But the main point here is that now, the point where the pebbles dropped in, there's zero information going upstream from this. So there's no communication between what's happening downstream and upstream. And this is for a Froude number equal to V flow over V celerity wave. We said they're equal to the same, so this is equal to 1. And so by the same token, so this is the same as screaming into the wind that's traveling at the speed of sound. If it's traveling at the speed of sound, no one will hear you downstream. You'll get blown away, of course, but no one will hear you. That's exactly the equivalent of this. Something's trying to move something upstream, but the airflow is going downstream just as quickly as Vs and V flow, exactly the same in the opposite directions. And so the case where V flow is much greater than Vs, what's that look like? First one is here, second one is here, third one is here. If you think about these ripples radiating outwards, and the fourth one look like this. Pretty cool. So this would be Fr greater than 1, and this is supercritical. So now the information that is downstream has no chance of being transmitted upstream. And so that kind of relates to these behaviors. And so the Froude number is the way of just defining these. So it's an important number in free surface flows. When you make a bow wave at the front of a ship, you lift up the water. You're acting against gravity, so you're expending effort in pushing against the ship. And so the ratio between getting that water away from the nose of the ship by having it radiate outwards, if the ship's going very quickly, the bow wave builds up very high and you have to use a lot of effort to get past it. If you're in supersonic flight, then the wave velocity you're talking about is not a wave in water on a free surface, but the acoustic wave by which you're hearing me, and it can't get away from the nose of the plane. And so you have to build planes for supersonic flight that are much stronger because it can't get the energy away from the aircraft to radiate acoustically away into the far surface. So esoteric stuff, not on the test, but fascinating, I think. Don't you think? That was just I saw there was no passion in that head nod, but that's fine. Great, that's all I got for you. So maybe we'll finish this off on Friday. We'll talk a bit maybe about how some of the things we've talked about in this class fit into the things that you have going on in your careers and will have going on in your careers, how it ties in, because this is kind of a lead-in course that makes, hopefully, some of that makes sense. Great having you here. Stay warm. Sorry to have overrun by 2 minutes.